So welcome to my talk. My name is Anjorin, and I'm a PhD student at the Technische Universität Darmstadt at the Multimedia Communications Lab. So I'll be presenting this work. So the motivation of our work is learning on the internet. So when we have an information, we usually go to the internet, and we go to a blog, go to YouTube, or to Wikipedia, the forum, or we simply check in Google what we find. And as we know, there are notorious things out there that distract us on the internet, like Facebook, and then after a while we don't know what we were looking for and what we found, and so you get lost with all the information out there. So this is the motivation for the work, and this form of resource-based learning is mostly self-directed, so you're in charge of the learning process. And this is the motivation for the Crocodile platform. It's a platform supporting resource-based learning, and it's my application scenario. Crocodile offers semantic tag types to give more information. So when you tag a resource you have found, you can also say what type it is. Activities to structure your learning, and you can form learner groups and friendships. And we offer recommendations, and this is my focus here. So this is the overview, the motivation with Crocodile, and I'll be analyzing Crocodile's structure to be able to say which recommendation system we can create for Crocodile. So, a taxonomy model can be described as a quadruple. So we have the users, the tags, and the resources, and the connections between them. So when a user finds a resource and attaches a tag to this resource, we then form a structure, and this is called a taxonomy. So we know this from social bookmarking applications like Delicious, Mendeley, Last.fm. So Crocodile extends this taxonomy model. So Crocodile has users, tags, and resources, but as well we have tag types. So this gives a semantic to the tags. So for example, research talk is suddenly now an event in association with these resources. We have activities as well. So activities give a structure to what we are trying to learn. So for example, while preparing this talk, I had an activity prepare talk, and there I had a sub-activity find related work, and when I found a resource out there on the internet, I attached it to these activities. And users can as well be attached to activities when working on this activity. And this as well is complemented by friends that we have on the platform, or we could build a group to work on a common activity. So all this information in Crocodile that extends this taxonomy model have been formalized in this paper, where we now describe the different elements that come to the taxonomy. We have the users again, we now have the tags for the types, we have the learning resources, and we have these new relationships between the elements, like the tag assignment is now typed, and we have this sub-activity relationship. We have the activity assignment relationship, that means assigning a resource to an activity, and the membership relationship, the activity, groups of learners, and the friendships. So back to the problem, we have Crocodile. It helps resource-based learning. So you have an activity in the middle, and you have on the left your activity structure. And while working on this activity, we provide recommendations. So that's the right option. So now we will look at how these recommendations are made. So after looking at all the structure of Crocodile, that it's a taxonomy model, we decided on a graph-based recommender system. So graph-based recommender techniques can be classified as neighborhood-based collaborative filtering approaches. It basically takes a graph, you define the items in the application as nodes and the relationships between them. as the edges between these nodes, and you define weights between these, for these edges and for the nodes. Then you apply a graph-based ranking algorithm, and you get a list of scored items or resources, and this forms now the recommendation list. So particularly for a taxonomy, you form a taxonomy graph, and there it's defined how the weights on the edges are defined, for example, between a user and a resource is the number of tags the users applied as attached to this resource. Then, for example, we have bulk rank as a ranking algorithm, a standard one for taxonomies, and it's based on the random walk of PageRank. And this means that the weights of the edges and the nodes in the graph are used to probabilistically determine how important a node is in the graph. So if you're a node that has many edges leading to you, you become more important. And the score is how often this algorithm visits this node due to these probabilities. So we now look at the two approaches we propose. The first one is A-score. So we extend the taxonomy graph with activities. So we add these activity nodes to the graph. That's the first step. Then we add the edges. So we have some new edges. For example, when the user attaches a resource to an activity, these forms new edges. Then we have the assignment of a user to an activity. This forms a new edge as well. And then the activity hierarchy. And the weights to the edges, we follow the standard taxonomy approaches, graph-based recommender approaches for taxonomies there, and we had to make some assumptions. For example, that the weight between a resource and an activity, as in when a user attaches a resource to an activity, is probably stronger than when a user attaches a tag to an activity. So that's why we take the maximum weight between a tag and a resource. So then after determining these weights on the edges, we now run a graph-based ranking algorithm, for example, bulk rank, but we could use any other graph-based algorithm. An A-inherit score leverages the activity hierarchies to calculate the scores. So here we don't depend anymore on a ranking algorithm that we finally apply after forming the graph. While forming the graph, we already calculate the scores. So we do this by taking all the tags a user has, and for each of these tags, we then select a part of the graph, depending on this tag. So for example, the green tag, research talk, is now selected for this user, and we then consider all resources directly attached to this tag, or for example, the activity structure attached to this resource that is attached to the tag, and through this structure we then find other resources in the activity tree and other users in the activity tree. We assume the scores due to the distance between the activities, because of course the further away you find the resource, the less relevant it is to the user and to its tag. So here we use the activity distance between two activities as the number of hops between them. So we now go to the evaluation part. So we decided on the GroupMe data set, as it has a substantial number of users and tags in the system and resources, and it has a similar concept as Crocodile, as it allows the grouping of resources. So resources that are semantically related to each other can be grouped together. And this is similar to the idea of an activity in Crocodile. And we use the mean average precision as a metric. This is the precision over several queries, for example, several users. And the precision is just basically how many items that are recommended are actually relevant. And we propose a new metric, the mean normalized precision, because when recommending items, it's important to be able to evaluate the top 10, for example, because the user doesn't check whether something interesting is coming in the 80th position. So this is why we propose precision at K. So we limit the scope, and to fit our evaluation methodology, we also provide the normalized precision. So the evaluation methodology we used, as this was using historical data, and in information retrieval we have the standard leave one out. So you leave something out and try and recommend it back. So here we have leave post out, which is a standard for taxonomies, where you remove all the connections between a user and a resource, and you try and recommend this resource back to this user. So we noticed that it's very difficult having the user as the starting point to find this resource when compared to having a tag as the starting point, because this tag might still be directly connected to this resource somewhere in the graph. And this is what motivated us to propose this new evaluation methodology, leave LT out. So we leave now the connections between a resource and a tag out. And this has the opposite effect. That it's now easier for a user as a starting point to find this resource, to recommend this resource to the user. And it's difficult or more difficult for the tag Tango, for example, to recommend this resource, starting with this tag. So we will see how this affects the results we have. So the results we visualize as a violin plot, because we find this method is very easy to follow. So it's a combination of a box plot and a density trace, but because we don't know what a box plot and a density trace is, I'll explain it here. So you see the density trace as following the curve. So this is actually a horizontal curve, but tilted vertically and reflected, so it looks better. And we have the median at that point, which shows that the median of the data is already at that point, which shows it's very good. That means the first quarter is already at the very low positions. So maybe the top 10 have all results already. And the higher you go, like in the 100th position, you start recommending less and less things. So this is the perfect shape we are trying to achieve with the data. So the evaluations, first for leave post out, where the connection between a user as the starting point and a resource left out. And popularity is just the number of tags on that resource, the number of resources, the user tags. And we see that popularity doesn't perform well at all. And then we have forecast, which is the standard graph-based approach for taxonomies, which performs quite well. And we see an adaptation considering the groups in this data set, group me, which was is also in the literature. And this is A-score, our approach where we consider the activities in our application scenario. And we have G-rank, which is also created for the group me data set that we used as an inspiration for A-inherit score. So as we see, A-score performs quite similar to G4 prime and A-inherit score to G-rank. So here are the results for the mean average precision and the mean normalized precision, which shows the top 10 values. And here we see that G4 prime and A-score perform best, and G-rank and A-inherit score less, and popularity in 4 rank the least. So here we have leave RT out. So this was the second evaluation scenario where the relationships between the tag and the resource are removed. And here we see that, for example, for A-inherit score, this is a harder task to solve as we use the tags of the user to evaluate this. And we see that A-score and G4 can perform best. And here are the results again. And in this case, A-score was actually statistically more relevant than G4 rank. And we see G rank and A-inherit score actually be worse than 4 rank at baseline. So, in conclusion, we have seen that exploiting the hierarchical activity structures as found in crocodile can improve the ranking of resources. We have proposed A-score and A-inherit score. And future work, of course, is to take the crocodile data set and now evaluate it on this data set, because we do hope that the activity structure in crocodile will be more fitting to our approaches as the grouping data set, which was actually groups of resources and not this learning context. And of course, with historical data, you can only say what happened in the history. So if a user did find a resource, then you can say, okay, that was relevant. But we don't know any other resources that we do recommend that these could be interesting as well to users. So of course, a user study would be interesting. We are working on integrating A-score and A-inherit score in crocodile, and then we will run the user study. And of course, graph-based approaches allow hybrids to be built. So for example, you can combine content-based approaches in the graph to form the weights of the edges, or you can even integrate a taxonomy to give more information to the graph structure. Or for example, we can take into consideration the user relationships, and so we have new edges in the graph. So, thank you. Yes.
I was wondering why that
yes, tag types have been researched into at my lab before I came, so I've taken over that. We did present one or two approaches using tag types at the INO conference. This work is just for activity because I'm taking every special case of crocodile, as in the semantic information found in crocodile. So this paper is focusing on the activities. I find the activities very interesting because they are based on a pedagogical concept that a learner actually has to consider, what am I working on, what tasks do I need to solve, and actually putting the efforts to break these down. And when attaching a resource, I find it's more important to attach a resource to an activity than to tag it, because the activity means much more to the user. Yeah.
So, actually, it's an important question. I think activity is an interesting mechanism which might allow the educational mechanism to distinguish themselves. So, part of it, there is some specific education, right? That education mechanism can take into account and do better than the generic algorithm. Otherwise, it can be up to the generic algorithm. So, do you have any secret platform in addition to the activities which might be helping the algorithm to perform better in the education context, not like the generic algorithm like Google education? What are the secret things which will make you do better?
Well, for example, in the movie industry, usually similarity plays a strong role. Content-based approaches are best there, or collaborative because you rate things. In this scenario, crocodile, we don't have that much data, so we have very sparse data. We have the phenomenon that users usually form very small groups. They work with each other just for a short period of time. So we have these cold start problems, and we don't always want to recommend similar things. And these are exactly the advantages of a graph-based approach, that it takes into consideration the structure that is growing there. You could even call it a knowledge structure, because the user implicitly tells the relationships between things. And if we use this, I believe it should perform better for this learning scenario.
When you look at group process, and we present our approach based on the crocodile terminology, how do you go about I said the group is just really involved, how do you talk these two activities? So how you take photos for any group of this way environment and you know how this level of organization, so what is the difference?
It was a big challenge. Finding data sets is very hard. I did consider, for example, Delicious is also having this concept of a stack. So you have resources that you also put in stack together. But Delicious just started with that, and I didn't find a publicly available corpus at that time. Crocodile as well is in a huge project, and we don't have enough data that it can be really statistically relevant. So that's what motivated me to look around. And GroupMe, I found through the literature that it has a taxonomy and used these graph-based approaches. And then I noticed that the groups actually, they group resources together with the aim of keeping them semantically related to each other. And in the application, they also view this group as a resource and further can tag it. So for example, that is not possible in Crocodile. The activities are tagged again. So for example, that was left out. So I mapped the two of them together. So users were learners, and the resources were resources, and the tags were tags, but the groups of resources were then the activities.
Thank you very much.
Thank you.